and books. Dr. O. Patmaraj has received awards like Dr. Kothari's Doctorate Fellowship Award by UGC at 2018, received his National PDF from DST at 2016. We are very happy to have you here, sir. We are welcome you to give the session, sir.
Thank you, sir. Thank you for giving a brief introduction about me.
Thank you, sir.
Thank you.
Again, sir, stop sharing and. Yes, sir. The screen is visible.
Yes, sir.
Please
yes, sir. Yes. Good morning to research scholars and professors. So once again, I would like to thank the organizing committee members for giving me a wonderful opportunity to share my research activities in the FDP program, especially on nanoscience and nanotechnology. Okay. Already Dr. Mahendran sir gave the brief introduction about my research careers, and then no need to introduce myself again. So directly I'm going to start my presentation. Okay. So today I am going to share my research activities in the field of nanostructured materials for lithium and metal air batteries. Okay. So before going to my research careers, first I would like to give the basic ideas about the battery and what is the concept that is behind the battery. Because actually in our day-to-day life activities, so everyone have been using the batteries for different applications. So I will use this platform to share my research activities and also to just to teach the concepts behind the battery performance. These are what principles of the battery. Okay, so now I am coming to the content of my presentation. Okay, so here actually I have written many things in the content part. Okay, so no need to fear, so I will complete as soon as possible. Okay, so first things I have given only the basic thing, that is a motivation of my presentation, then basic concepts of cells, then our batteries, then components and its operations. What are the components are existing in the cells or battery, then how it operates. Okay, then packing and configuration. So this is the most important things actually, packing and configuration. So even in our day-to-day life activities, we are using different shapes and different types of batteries for different applications. So before going to use the batteries in our application, first we should know the configuration of the battery. Then what is the packing? So what type of battery? So by seeing the packing itself, we could find out the what is the configuration of this battery and what type of batteries are available in the market. So everything actually you will see in this packing and configuration. Then classifications of batteries. Okay, so we know that two types of batteries will be there. Then how to classify this batteries. So everything we will see in the classification of batteries. Then rechargeable lithium batteries. So what are the rechargeable lithium batteries are available in the market, and what is the merits and demerits? So we will see in the coming slides. The challenging of the lithium batteries. So what is the challenging? So right now, actually, many issues and challenges are going in the rechargeable lithium battery. So how to overcome that issues? Okay. So what are the things actually we need to focus as a researcher? So I will highlight all the issues, and so based on that, actually I have developed some nanocomposite polymer electrolyte for lithium batteries. So I will share my research experience regarding the nanocomposite polymer electrolyte. Then a fabrication of Cr203 point cells, actually use the developed membrane. Then I will show the electrochemical performance of the fabricated cells. Then battery testing and performance. Okay, so after fabrication, we should know the parameter. That means we should know the specification of the battery testing and performances. Then emerging battery technology. This is the most important thing. Okay, so we know that even various types of rechargeable batteries are available in the market now. Just 2 years, just 5 years back. So now the emerging battery technology is has been increasing the interest to develop the metal air batteries. Okay, so what is the issues and challenges existing in the metal air batteries? That is a new emerging battery technology. And what is the mechanism behind this metal air batteries? So what are the things we have to focus to work on the issues? So all the issues I will highlight it. So based on the issues, how to choose the problem. So this is the most important thing, because actually this FDP, I heard, I think many of the research scholars are participating in this FDP. I think they will get idea, or they will get the motivation to develop the novel materials of the emerging battery technology. Understood. So first I will highlight the issues and what are the challenges, what are the things actually we have to do we have to do to work on the issues. Okay. So some of the challenges actually I will highlight based on my research experience. The development of hydrophobic polymer electrolyte fibrous membrane and development of non-precious bifunctional electrode catalysts for overcoming the existing issues, especially in the emerging battery technology. Then I will give the summary of my presentation. Okay. So if you are having any doubt, please note down at the end of my sessions and please ask me. Okay. So even at that discussion time, actually will clear our doubt. Okay. So now I am coming to the motivation of my presentation. Okay. So nowadays, we are concerning about the shortage of fossil fuels, environmental pollution, and global warming. Okay, so even day-to-day life also we are suffering petrol or diesel cost hike, then gas cylinder, that is a gas also cost also is hike. So due to the shortage of fossil fuels, and last week also then highlighted news also came regarding the global warming. So nowadays the temperature of the earth is increasing due to the global warming. So due to the environmental pollution. So this is the major concerns actually. So all researchers, all scientists have been focusing to control the environmental pollution and to control the global warming. So as a researcher, actually we need to find out the alternative sources. Okay, so we know the shortage of fossil fuels. So in our day-to-day life activities, we are using the fossil fuels. What are the fossil fuels? Oil, coal, and natural gas. We know. So here, see here, this energy demand projection in India. See here, 1991 to 92, and 2009 to 10, and 2020 to 41. See here. So how fast the demand is increasing compared to 91 to 92. See here. So here the last one, the color was in 2021 energy demand projection in India. So due to the shortage of fossil fuels, actually, so as a researcher, so what we have to do, we have to find out the alternative available energy sources. Okay, that is eco-friendly energy sources. So based on that, researchers has been focusing to develop a renewable, eco-friendly energy conversion and storage devices as an alternative available energy source. Includes batteries, supercapacitors, fuel cells, and solar cells. So in this field, okay, many researchers, okay, even worldwide, researchers have been focusing to develop the novel materials of energy conversion and storage devices, especially for the nanostructured materials to increase the cycle life, to increase the efficiency for practical applications. Understood? Now, actually, everyone looking for them small size. Okay, so even in compact, even in small size, how we have to increase the energy density. How we have to increase, how we have to utilize the energy device for applications. So if you develop the big devices, then we cannot utilize that instrument for the particular. We cannot utilize the device for particular instrument. Now we are looking for the compact and portable. So now actually worldwide, so everyone is having the portable things. Understood. So everyone is using mobile phone and laptop. So that one is very easy and comfortable to pack the device in our bag also. So there is a need to develop the renewable, eco-friendly energy conversion storage devices and alternative source. Okay. So that's why actually. So I am focusing on battery. Okay. So to work on the shortage of fossil fuels, environmental pollution, and global warming. Understood. So we know that various renewable energy sources are available. Okay, we know that. So many resources are available, renewable energy resources are available around us. Okay, so based on the working principle, the renewable energy resources can be classified into four. That is a mechanical, chemical, electrical, and electrochemical. See here. So among the energy devices, so here actually we are here red color highlighted here. This is for energy conversion and the storage devices. There is a battery, supercapacitor, solar cells, and fuel cells. So I am going to focus. I am focusing on batteries, and also I am going to share my research activities related to the batteries. That is energy conversion and storage devices. Okay. So before going to the cell, or before going to the operation, before going to the electrochemical cell, so first we should know the basic things. Okay, so what is the basic things we might have studied in our school level? Okay, so even college level also we might have studied the basic galvanic cell, Bell cell, electrolytic cell, and electrochemical cell. What is the basic difference between the galvanic cell, electrolytic cell, and electrochemical cell? We are focusing on the electrochemical cell. Why? That is the redox reaction. Okay, spontaneous redox reaction through that is chemical energy conversion into electrical energy, or electrical energy converted to chemical. That is vice versa reaction is happening in the electrochemical cell. See here in galvanic cell, chemical energy converts into the electrical energy. So there also spontaneous reaction will be there, but in electrolytic cell there is no spontaneous redox reaction. So we have to apply some external source to do the reactions. That means charging. And so we have to apply some external force. So that is the basic difference between the galvanic cell and the electrolytic cell. Here in electrolytic cell, actually we have to use only the two electrodes, that is standard electrodes, zinc and copper. But in galvanic cells also, dissimilar electrodes also we can use it. So here in galvanic cell, what is the difference? The anode is negatively charged and the cathode is positively charged. But in the case of electrolytic cell, the anode is positively charged and the cathode is negatively charged. That is the basic difference. So here the electrochemical is the combination of galvanic cell and electrolytic cell. That is the chemical energy converts to electrical energy. Then vice versa, electrical energy again converts to chemical energy. So this is the basic difference between the galvanic cell, electrolytic cell, and the electrochemical cell. Okay. So now I am coming to the cell. Okay. So what is the definition of cell? Okay. A single electrochemical cell, a cell containing one anode, one cathode, and electrolyte. This is one cell. So what is the difference? What is the difference in battery? So what is the difference between cell and battery? So battery is nothing but there is a collection of cells. Clear? The cell is a single electrochemical cell that is containing only one anode, one cathode, and one electrolyte. Suppose I am making the combination of cells, so that is called as battery. A collection of cells are connected in series or parallel or series parallel based on our requirements, based on our applications. Understood? If you are connected in series, what will happen? The voltage will increase. If you are connected in parallel, the current will increase. So based on our application, based on our requirement, so we are connecting the cells either in series, parallel, or series parallel. Clear? So here I am showing. Here I am I am showing the pictures. So how to connect the series and how to connect the parallel connection. Okay, these are the batteries here. 1.2 volt battery. There is each batteries are 1.2 volt and 1000 milliamp. So if you are connecting the battery in the series connection, so what will happen? How to connect the series connection? That is negative, positive, and positive connected with the negative of the second battery, then positive connected with the negative of the third battery. So like that series connection you have to do. So by doing the series connection, we will increase the voltage. Okay. So based on our applications, suppose I want a 4 volt, 6 volt, or 2 volt battery. Understood? Even actually, so in our industry or in our home also, we are using the UPS or inverter. Okay, how to increase the voltage? By connecting the series. How to increase the current? By connecting the parallel. So the combination of series and parallel, so we are fulfilling our basic needs. Understood? So this is the basic things. Understood? So suppose I want to increase the current. So here 1000 milliamps for each battery. So suppose I want 5 amps. I want 5 amps for my application. So just connect it 1000. If you connected 5 batteries, what happened? That is 5000 milliamps. Okay, that is a 5 amps. Understood? So this is the combination, series and parallel combination. That is a increasing voltage as well as the current. Okay. So now I am coming to the electrochemical cell or battery. Okay. So the cell or battery. So that's just first, that's different, the basic difference cell and battery. Okay. So now I am coming to the definition of the battery. That is, a battery is a device that converts chemical energy into electrical energy or electrical energy into chemical. That is vice versa through the redox reaction. Redox reaction. What is a redox reaction? That is a reduction and oxidation reaction happening, that is occurring between the two dissimilar electrodes. Okay. So already I told you, in cell, two electrodes will be the one is anode and one is the cathode. Okay. That two reactions, that is a reduction and oxidation reactions occurring at two different dissimilar electrodes. Clear? Okay. So now second, so in an electrochemical cell, that is the electric potential E is created between the two dissimilar electrodes. So that two electrodes we are going to use in the cell, that two electrodes having dissimilar, that is a different electric potential. Okay. So how to find out the electric potential? What is the definition of electric potential? Okay. So I told you reduction and oxidation are two different electrodes. That is oxidation potential and reduction potential. Oxidation potential at anode and reduction potential at cathode. So what is the potential? That means that is the ability to lose the electrons at the cathode. So that is the potential of the anode. Okay. So what is the cathode? So the cathode has the ability to gain the electrons. Okay, these two electrodes having different potential. Okay, so based on this potential, we can calculate the theoretical cell voltage. Understood? So this is the most important thing. So how to find out the specification of the battery? Suppose I am making one battery. So how to find out the specification of the battery and the current? Okay, that is specification of the battery means that is a voltage. Okay, so first we have to calculate the theoretical cell voltage. Then if I am connecting the series connection of the cell, then I can calculate the overall voltage. If I am connecting the parallel connection, if I am connecting the parallel, so I can calculate the current. Okay, so this is the standard format to calculate the theoretical cell voltage of the battery. So here already I told you two reactions will occurring. Okay, the cell having the two of reactions. Okay, oxidation of reaction and reduction of reaction. Oxidation reactions occurs at the anode, and the reduction reactions occurs at the cathode. Okay, that is oxidation of reaction, oxidation. So here, for example, here I am giving on the reaction also. What have a zinc electrode? There is a zinc electrode. There is zinc plus 2 electrons is releasing to the zinc electrode. This is zinc 2 plus ions. Then copper electrode. Okay, so in electrolytic cells, you know that zinc and copper 2 electrodes will be there. In the beaker, electrolyte solutions will be there. Okay, so next slide I will tell you what is the electrolyte. So here I am telling the electrolyte solution. The electrolyte solution is nothing but zinc sulfate and copper sulfate. That is the zinc ion and copper sulfate ions. Okay, so the salt we are dissolving in this. So what will happen there? Ionization will be there. That is ions will be there. Zinc ions and sulfate ions will be there. That is electrolyte. So electrolyte is a medium to transfer the ions from one electrode to another electrode when the electrons transferring through the external circuit. Okay, so two dissimilar electrodes will be there. These electrodes try to attain the neutralize. Then electrons is releasing from the anode and electrons gaining from the cathode. So when the electrons is transferring to the external circuit, the ions is moving from an anode to the cathode or cathode to anode. That is vice versa reaction is happening through the redox reaction. So these two off reactions is occurring in the electrochemical cell. Okay. So already told you how to calculate the theoretical cell voltage and oxidation potential. So this is the standard electrode potential. So based on this standard electrode potential, so we can calculate the cell voltage. That means the standard potential we know, anode and cathode potential. So from the cell voltage also we can calculate. Now I am coming to the components of the cell. Okay, components of the cell. So already I told you the cell containing one anode, one cathode, and electrolyte. So cathode, anode, electrolyte, and separator will be there. What is the role of separator here? So here I am seeing this slide. Actually, I have given one picture also. The picture. So this is the morphology picture of the commercial separator. Okay, that is the same images of the commercial separator. So this commercial separator or filter. So it is available in the market. So how it is looking like? So even the separator also can be classified into two types. Okay, so based on the battery applications. Okay, that is a monolayer and triple layer. So what is a monolayer and triple layer? So monolayer, that is a making polypropylene separator. That is a tri-layer means that is in between, that is like sandwich type. Okay, that is a top and bottom layer, the polypropylene, and in between the top and bottom, one polyethylene layer will be there. That is polyethylene membrane will be there. That is a tri-layer. Understood. So, what is the unique property of the tri-layer? Understood. So, what are the materials are available in the market? First, we should know the basic properties of the material before going to fabricate or before going to use the battery. Suppose we are using the battery. First, we should know the components present in the battery and what is the operation, what is the function of the component. Okay, so what is the function of the components and what is the separator? Why we are using the separator? So, if separator, how it look like? Okay, so here the tri-layer separator I told you. So these attractive properties will be there. Understood? Suppose see during the operation of the battery, that means during charging and discharging. Okay, so that's why I'm telling the operation. During charging and discharging, what will happen? That internal temperature is increasing in the battery. What will happen due to the internal energy? The separator, even electrolyte also may possible to decompose, and the separator also may possible to shrink. Understood? To shrink. Okay, due to the internal temperature in the battery. Understood? Even actually we have seen in many batteries using in the mobile phone also. Actually, some batteries are bulged at the center. So, what is the reason? What is the reason? Anyone can tell me? You know that? What is the reason? The batteries we are using in the cell phone. Okay, so after 1 year or 2 years, we can able to see the batteries in bulged form due to the electrolyte evaporation. Okay, that is during the operation, charging and discharging. Suppose many cycles you are doing the charging and discharging. What will happen? The internal temperature will be there. So due to the internal temperature, the electrolyte gets vaporized. So that bulge is nothing but the vaporization of the electrolyte. That's all. So due to the internal temperature, the separator may possible to shrink. So in order to avoid that, if the separator just shrink means what will happen? There anode and cathode get short circuited. So then the battery gets explosive. So that's why. So even our so many scientists actually informed us to while charging, don't talk, don't use. Okay, just to unplug the mobile phone from charging, then you speak to someone, then you use it. Okay, so while charging, if you are using the phone, what will happen? There already charging will be there. Okay, then charging means what will happen? Then reaction mechanism is happening. Understood? That means electrons moving from the cathode to anode, the ions is moving cathode to anode. That is charging process is happening. So at the time, if you are speaking, what will happen? There discharging process is happening. So simultaneously, charging and discharging process is happening. Understood? So what will happen? Automatically, internal temperature is increasing. So due to the internal temperature, the separator gets shrink. Then both the electrode and anode gets short circuited. Then mobile phone gets explosive. Okay, that's why the researcher, the scientist informed us, don't use the cell phone while charging. Clear? So this is the reason behind that. Okay, that is the role of the separator here. So separator, that is separating the two electrodes. Okay, to avoid the short circuit. Okay, if separator gets shrink, automatically short circuit will be there. Then your mobile phone gets, that is your battery gets explosive. Understood? Then electrolyte. Electrolyte is a medium to transfer the ions. The anode under oxidation reaction occurs at the anode, and the reduction reactions occurs at the cathode. Understood? So this is the cell construction here. See here, this is our container filled by the electrolyte. Electrolyte. I think someone is talking. See here, electrolyte and anode, cathode will be there. So in between the separator will be there. So this is a separator. That is a separator is separating the two electrodes to avoid the short circuit. Here, electrolyte. So during when the electrons is transferring the anode to cathode, the ions is moving through the electrolyte. So this is the function and this is the operation of the components present in the battery. Okay. So now I am coming to the packing and configuration. Okay, packing and configuration. Okay, what is the packing? So in our work, in our day-to-day life, okay, so in our day-to-day life, we are using variety of batteries for different applications. Okay, it's a packing state. So some batteries are looking like cylindrical, some batteries are looking like rectangular, some batteries are looking like pouch shape. Okay, so different types, different shapes of batteries we are using in our day-to-day life activities for different applications. So first we should know this. First, we should know the basic things. So, what is the configuration of the battery? So, how to pack the battery? Okay. So, in these slides, we are going to see the packing and configuration of the batteries. Okay. So, this tabular column indicates the type and size of the batteries. Okay. So, even actually, we are buying batteries. What is it in shop also? The AAA battery, AA battery, even a single A battery, 9-volt battery, 4-point, different types of batteries we are buying. Okay, so what it indicates? Suppose we are using the AA battery or AAA batteries in our wireless mouse or in remotes, in our TV remote, we are using the AAA battery or AA batteries. Okay, okay. See here, what is the size? See, 14.5 into 50, that indicates the AA battery. Okay, that means everything is mm, 14.5 mm and 50 mm will be there. Okay, so WA indicates the size of the battery. Understood? So simply we have to say WA battery means that size, that is 14.55 into 50 mm. The AAA battery means that is 10.5 mm into 44.5 mm. So this number, okay, indicates the different types. This F means 33 into 90 mm, big size. D bat, C, B, A, AA, AAA, and 4A also is there in water. 8.3 into 42.5. That is a very, 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 very small. That is a small cylindrical battery. That's true. So different. This is this tabular column actually indicates a different configuration of the batteries. Okay. Now I am going to show the pictures of cylindrical cell and what is the merits and demerits. Okay. So how the cylindrical cells are constructed. Understood. So here cylindrical cells. Okay, different types of cells actually we are using, we are purchasing in market. Then cylindrical cells I'm coming to tell you. So the cylindrical cells is this the picture of the cylindrical cells. Here the cylindrical cells contain the rolled type of the anode, electrode, and separator. Okay, that is the stocking of the anode, cathode. Stocking of the anode, cathode, and the electrolyte just rolled and inserted into the cylinder. That is the chamber. Okay, the cylindrical type chamber will be there. Okay, so what is the merits and demerits of cylindrical cell? So the merits, the classic packaging for primary and secondary cells, high mechanical stability, economical, long life. So the third most important thing, holds internal pressure without deforming case. So if internal pressure is increasing during the operation, so it won't come out because the container, the cylindrical cell, the cylindrical containers will be there. That is metal container will be there. So the metal container which holds the internal pressure without deforming the cases. So that is the merits of the cylindrical cell. Okay, and one more thing, that is packaging. That is classic packaging for even both primary as well as the secondary cells. Understood? Even by stocking the anode, cathode, and electrolyte separator, even we can increase the capacity of the battery also. That means the mass of the active material, if you increase it, that is the length of the roll also. We can increase by increasing the length of the roll also, we can increase the capacity of the battery. Understood? So what is the demerits? That is inefficient use of space. We cannot use in all the spaces. We cannot use in our mobile phone also, because actually we are using a mobile phone very thin. So if you are using this cylindrical, so it occupies more space. So even actually in the laptop also we are using the cylindrical cells. Okay. So even the series connections we are connecting, and parallel connection also is there in our laptop. Okay. So that is a demerits, inefficient use of space, and metal housing has to weight. So due to the metal case, that cylindrical case will be there. So it will increase the weight of the cell. So these are the demerits of the cylindrical cell. And what is the merits and demerits of button cell? Okay, so button cell we are using in our watch. Okay, even the laser light, also we are using. Even different portable toys also we are using the button cells. Okay, so what is the merits and demerits of button cells? Okay, so also known as coin cell. Button cell also known as coin cell. That is very small size, easy to stack. Okay, but here easy to stack means here there is sandwich type we are stacking here. That is nano, then the separator, electrolyte, and cathode. Just stacking like that. Okay, it is look like a coin. It is look like the coin. So mainly reserved as primary batteries in watches and watches. Okay, what is the demerits here? Rechargeable buttons do not allow fast charging. Understood? Do not allow the fast charging. What is the reason? Here, that stocking is very. What is that? Stocking is very minimum. Okay, so only that is one stacking. Maximum is two stacking only is possible. So here stocking is a minimum. So even recharging also. So it will take long time. Even that is output of that is the capacity of the coin cell also is very less because of the low active material will be there. Okay, that is a demerit. That is a limited and new development. Okay, so must be kept away from the children. Harmfully swallowed voltage. Okay, so this one is very small and easy to handle also. Even if you keep it outside also, even children also possible to misuse that coin cell also. Okay, so prismatic cell. So what is a prismatic cell? The prismatic cells we are using in our mobile phone. Even nowadays pouch cell also is coming. So prismatic cell. That is the best usage of space and allows flexible design. So what is a flexible design? Here the electrodes can able to flexible, can able to fold it, can able to rotate it. Okay, that is a flexible electrodes will be there in the prismatic cell. Understood? So what is the demerits here? Higher manufacturing cost, less efficient thermal management, and shorter life. This is the demerits of the prismatic cell and pouch cell. Okay, so totally we seen the 4 different types of cylindrical, the cylindrical and button cell, prismatic, and pouch cell. So pouch cells here. So I asked, this is the one bulged one, pouch cells. So the pouch cells also we are using in our mobile phone. That is a light and cost effective to manufacture. So here there is no metal case will be there. Only the aluminum foil will be there. Only the aluminum foil. So this one easy, that is lightweight and we can use in small space also. And it's a simple, flexible and lightweight solution. So what is the demerits here? That is exposure to humidity, hot temperature, short life. Okay. Suppose we are say we are using the aluminum foil to cover the battery. So there is possible to explore the possibilities to explore with the humidity. That is to explore with the normal atmosphere. Okay, there is possibilities will be there. That is the demerits. Understood? Then hot temperature, shorter life. So due to the temperature, due to the internal temperature, here the electrolyte gets purged. The electrolyte gets vaporized. So due to the vaporized, this one, the size of the battery is purged. The loss of stack pressure is swelling due to gassing. So design must include allowance for 8 to 10% filling. These are all the demerits in the poster. So now I am coming to the series connection and parallel connection. So how to connect the series then how do not connect the series. That is a good string and faulty. Understood? Suppose 4 batteries we are connected in the series. What will happen here? So the batteries, even one battery, even all the batteries should be in working condition. So if you connect it, then your output will get 4.8 volt, then 1000 milliampere. Adding cells resisting increase the voltage, same current. Then faulty things. Okay, out of the 4 batteries, if one battery gets faulted, what will happen here? That full voltage not available. So this one just will may cause failure to other batteries also. Here 1.2, here 2.4 volt. Here only the 0.63 volt will be there and 4.5. We won't get the full voltage. So this is the faulty things. Faulty cell wires overall voltage causing yearly cutoff. Weakest cell is touched most stack deteriorates quickly. So we have to find out the not working batteries and we have to replace it shortly. Otherwise, it will cause other failure of other batteries also. Okay, that parallel connection. Similarly, for the series, and the parallel connection will be there allows high current and same voltage. Then weak cell. So we have to find out this. Okay. Now series parallel connection will be there. So here one pictures will be there. So these pictures actually we are using in the laptop. So here cylindrical cells will be there by series and parallel connection. Here what is that, prismatic cell or pole cells will be there. The even here also in this case also even of cylindrical cells actually we are using by connecting series parallel combination. Understood? So based on our requirement, we have to connect the batteries by series or parallel or series parallel connections. Okay. So now I am coming to the classification of batteries: primary batteries and secondary batteries. We know that. Okay, for primary batteries we cannot recharge it only for single use only. The secondary batteries repeated use will be there. Then okay. Now I am coming to the primary batteries. Okay, that is what is the primary primary batteries nothing but non-rechargeable batteries, single. Even the non-rechargeable batteries hold more energy than the rechargeable but cannot deliver high load current. Understood? So here voltage will be there, but it won't current, it won't give the high current. The capacity is very less due to the lower active material. Okay, say Lagrange cells will be here. Then different cells I will be using for our applications also. Understood? Now I am coming to the alkaline batteries. So this is the AAA battery, AA battery, 9-volt battery. So all are the alkaline batteries. Okay, that is alkaline batteries, nothing but the primary battery. Okay, now this is the configuration of the primary batteries. Configuration of primary batteries. Okay, that is the chemistry of the primary. What are the batteries available in the market? That chemistry. That is a zinc carbon, zinc, yeah, alkaline, lithium batteries, lithium manganese dioxide, lithium ion dioxide. What is that in this chemistry? What is the anode? Zinc is the anode and cathode is the manganese dioxide. Then electrolytes. What are the electrolytes actually we are using? Of course, ammonium chloride or zinc chloride. Anode, cathode, and electrolyte. What is the cell voltage of the zinc carbon? 1.5 is the nominal and the end is the 0.4. 0.9, sorry, 0.9. That is a lower cutoff voltage. This is a higher cutoff. Maximum 1.5, lower cutoff voltage is 0.9. Okay, power density is low. So here, so among the available primary batteries in our market, see here the lithium-based batteries having high voltage and high power density. Also, even energy density also is having higher. Clear? So even the last picture also I showed you. So here, the lead acid battery, nickel metal hydride, lithium-ion batteries will be there. But compared to the rechargeable batteries, non-rechargeable, the lithium-based non-rechargeable batteries having high energy density, but low load current. So that is a drawback in that primary batteries. Okay. So even among the available primary batteries, lithium-based batteries having a high cell voltage. Even what is the anode? Lithium. So we know that lithium is more reactive. Okay. So by handling this lithium, so we have to we have to create some special atmosphere for the application. So that's why actually cost as expensive will be the lithium-based primary batteries also. And what is the electrolyte here? Non-aqueous, that is organic-based electrolytes, organic solvent, salt solution, organic solvent, EC, PC, DEC, BMC, even many organic solvents have been using for preparing the electrolyte solution for lithium-based batteries. Okay, so lithium ion dioxide. Okay, now I am coming to the secondary batteries. Okay, see here this picture. So what is that? Various rechargeable batteries are been available in our market. So among the available rechargeable batteries, lithium-based batteries having high energy density, even in size as well as the weight. Understood? That is even a small space and lightweight. Okay, small size as well as the lightweight. So compared to other rechargeable batteries, lithium batteries having high energy density. So because of the lithium. Okay, so here, see here, the secondary batteries, rechargeable cell reactions are reversible. The lead acid batteries, so available in market, nickel cadmium battery available in market, nickel ion battery, nickel metal hydride battery, lithium ion polymer. See here, what is the difference? 3 types of batteries are available in the market, lithium-based batteries. What is the difference? What is the difference between lithium battery and lithium ion battery and lithium ion polymer battery? So we should know the basic difference. So even lithium battery itself, actually 3 classifications will be there: lithium battery, lithium ion battery, and lithium ion polymer battery. Understood? So we should know the basic differentiation. So how to differentiate the lithium-based batteries? Okay. Then we should know the configuration of all the secondary batteries. Understood? The configuration, that is specification. I'm telling about the specification of the batteries, rechargeable batteries. So because we are facing variety of rechargeable batteries in our day-to-day batteries. Okay. So here this is the relation between the power and the energy for all the rechargeable batteries. Now, so this is the specification and configuration of the rechargeable batteries. What is the lead acid batteries? So in lead acid batteries, we are using in all vehicles. Okay, even bike or car, that is a two-wheeler and four-wheeler vehicles. Actually, we are using the lead acid battery. So what is the merit and demerits of lead acid battery? So before going to the merit and demerit, first I am telling you the configuration. What is the anode? Anode of the lead acid battery. So we are using the acid battery, lead acid battery in our car or bike. So we should know the components present in the battery. So that is the basic things. And as a researchers, okay, so we should know the basic configuration of the each battery. So anode, what is the anode? Lead. Cathode, lead oxide. What is the electrolyte? Sulfuric acid. What is the cell voltage of the battery? 2 volt. Understood? So we should know the working mechanism of the lead acid battery also. Even UPS also. So we are using UPS in our home. Okay. So in the UPS also we are using the lead acid battery. So without using also, why we have to switch on the UPS? Even per day or 2 days once we have to switch on. Understood? Just make a reversible reaction. That is charging and discharging. So automatically self-discharge will be there. So the self-discharge will be there. That means the lead becomes lead oxide. So by charging, what will happen again? The lead will be there in the anode. Okay, that is a reversible reaction. By applying the experiment, we are making the reversible reaction. Okay, that is a merit, high current density. What is a demerit? Toxic. So lead we are using and sulfuric acid we are using as an electrolyte. This is a highly toxic. That's why we are looking for the new rechargeable batteries. Okay, so even nickel cadmium battery. So what is the configuration of nickel cadmium battery? What is the anode? Anode is the cadmium, cathode is the nickel hydroxide. Okay, then electrolyte KOH, potassium hydroxide, cell voltage 1.4. So here lead acid battery is a 2 volt and compared to lead acid battery, nickel cadmium battery is lower voltage. Okay, so what is the merits and demerits? Here reaction mechanism also I have written here. See here, this is the reaction by the lead and sulfuric acid, lead sulfate will be there. Okay, the lead sulfate will be there. The lead sulfate will doing the discharging will happen. Okay, while charging again, the sulfate will go out, then again lead will be there. Okay, so the nickel cadmium battery here. So this is the configuration and this is the what is that? Reactions happening in 2 different electrodes. That is cadmium and nickel oxide, nickel hydroxide. Okay, what is the merits and demerits here? High cycle life and reliable compared to reliable. So this is the merits of nickel cadmium battery, but demerits lower capacity and lower voltage and toxic and memory effect will be there. Understood? Now I am coming to the third rechargeable batteries, that is a nickel metal hydride battery. So now first we should know the configuration of the nickel metal hydride battery. What is the anode? Metal hydride and cathode same like a nickel cadmium battery. But same voltage only here. Because actually anode and cathode is the same material, then we know that how to calculate the theoretical cell voltage. So okay, that is subtracting the electrode potential, that is anode electrode potential from the cathode potential. So we can calculate the theoretical cell voltage also. So what is the merits and demerits of the nickel metal hydride battery? Okay, non-toxic, high capacity and energy density approaches equivalent to the lithium battery. Understood? Then demerits, self-discharge and memory effect will be there. So that is a demerit. But even capacity is nearly equal to the lithium battery. Understood? Now lithium secondary battery and lithium ion battery. So what is the difference? So already I told you. So what is the basic difference between lithium battery, lithium ion battery and lithium ion battery? See here. So that's why actually I told you first we should know the configuration of the lithium secondary battery and lithium ion battery. So lithium secondary, what is the anode here? Pure lithium metal. But lithium ion battery, what is anode here? Carbon. So this is the difference. If you are using carbon as anode in the battery, so that is called as a lithium ion battery. If you are using lithium metal as anode, so that is called as a lithium secondary battery. Clear? So this is the main difference between the lithium battery and lithium ion battery. Understood? Don't get confused. So even actually if you are using lithium metal also as anode, so we call it as lithium ion. That is wrong. Okay, if you are using lithium metal as anode in the battery, so that is called as a lithium secondary batteries. If you are using carbon as anode, that is a lithium ion battery. But cathode is everything is same. So this is the standard configurations available in the market. Understood? So this is the successful configurations available in the market. So based on this configuration only, all the lithium based batteries are available in our day-to-day life. Understood? Even though, so even lithium manganese oxide is also will be there, lithium cobalt, lithium phosphate also will be there. So nowadays, actually, even cathode different cathode materials also that is emerged for practical application. That is for market purpose. Okay. So what is the electrolyte here? LiPF6, lithium hexafluorophosphate dissolved in EC and PC. What is that EC and PC? So there is organic solvent, EC ethylene carbonate, and PC is ultimate propylene carbonate. So why we have to make the combination? Why we are not taking only single electrolyte, single solvent? Do you have any idea? That is LiPF6 in EC and PC. So that is a mixed solvent, a mixed organic solvent. So in order to optimize the viscosity as well as the conductivity of the organic solvent, understood? So we are mixing the various proportion of two organic solvent, that is ethylene carbonate and propylene carbonate. So in that we are dissolving the lithium salts, LiPF6, lithium hexafluorophosphate. Okay, given variety of salts are available in market. Okay, so this is the standard one, LiPF6 in EC and PC. The cell voltage is 4 volt. So what is the merit? High energy density, lightweight, and most electropositive element. What is the most electropositive element? That is the lithium. Okay, because of electropositive element, so the lithium gives a high energy density, and anode, the lithium also is lightweight. So lightweight. Okay, so what is here demerit? Expensive. So we know that lithium is lightweight and rare one. Okay, so we cannot handle in normal atmosphere. So we have to procure the lithium material and just store in a special chamber. Okay, special chamber. That means to avoid the humidity, to avoid the reaction. So we have to store the lithium metal in the special chamber. That is low box we have to store it. Okay, in organ atmosphere. So that's why the lithium-based batteries are expensive and safe. So lithium ion also same problem, same property with ether, then self-solid ether. So what is the lithium polymer battery and lithium ion polymer battery? Similarly, so lithium polymer battery, here anode is a lithium, cathode is a lithium cobalt oxide, and electrolyte is the polymer electrolyte film, solid polymer. Even polymer electrolyte also can be classified into 3 types: solid, gel, and hybrid. Okay, so coming slides I will tell you what is the basic difference between the solid, gel, and hybrid. Okay, the electrolyte is a solid polymer films. What is the cell voltage? 4 volt similar. Understood? So what is a lithium ion polymer battery? Anode is a carbon, cathode is a lithium cobalt oxide, then electrolyte is a solid polymer electrolyte. That is the basic difference. So last slide I told you the basic difference between lithium and lithium ion. Then this slide I am going to I told you lithium polymer and lithium ion polymer. Understood? If you are using solid polymer electrolyte in lithium battery, that is a lithium polymer battery. So if you are using polymer electrolyte in lithium ion, so what is a lithium ion? That is anode as a carbon. Okay, carbon used as a anode means that is a lithium ion polymer battery. So this is the standard reaction. Okay, so how the reaction is happening at cathode and how the reaction is happening at the anode. So how to find out the cell potential? That is the cell potential, anode potential, then cathode potential. So we will get the overall minus. That is a subtraction. That is a electrode potential, subtraction of negative electrode potential from the positive electrode potential. What will happen here? Automatically 4 volt. So we know that the anode potential is minus 3 volt. So cathode potential is 1 volt. Just you subtract it, what will happen? So totally the theoretical cell voltage of lithium-based batteries having 4 volt. Understood? So this is the tabular column for configuration of the complete rechargeable batteries. Okay, here the lead acid battery, nickel cadmium, nickel material, and lithium ion. So anode, cathode, and electrolyte. Already I told you the configuration. Cell voltage here. So among the available rechargeable batteries, lithium-based batteries having high energy density, high cell voltage, and high power density. Okay, but safety issue is there. So we have to look for the safety issues, how to overcome the safety issues. Okay, so in order to avoid the issues, that is safety issues, so we have to focus some modification. That is, we have to do some challenges of rechargeable lithium batteries. Okay, so what are the challenging tasks will be there? Okay, so first one is the improvements in specific energy. How to improve the specific energy the rechargeable lithium batteries. Then second one is how to improve the specific power. Then third one, how to improve the safety and cycle. These are three issues be there. These three issues are existing in the rechargeable lithium battery. So we have to focus these issues and how to work on these issues. What are the things we have to do? Okay, to improve the specific energy by the modification of electrodes we have to do. So we know that anode and cathode electrodes will be there. So we have to do the modification and both the electrodes, anode as well as the cathode, for improving the specific energy. Then specific power, the determination of lithium diffusion in and out of the electrode structure through the electrolyte. So the improvement in specific power indicates the material structure. So why I am telling you, so we are focusing on the nanoscience and technology, the nanostructured materials for lithium batteries. So this is the most important thing. So if you are developing the nanostructured materials, we can increase the specific power as well as the energy density. Clear? So if you develop the nanostructured materials, so we can enhance the lithium diffusion in and out of the electrode structures through the electrolyte. That is a fast diffusion will be there. Then specific we can improve the specific power during operation. Then safety and cyclability. So two possible strategies have been using to achieve the safety results without sacrificing their energy density. Understood? So what are the possible strategies? Two possible. One is the electrode combination operating within the stability of organic electrolytes. We are using the electrolytes. Okay, the organic electrolytes. What is the stable? So first we should know the stability of the organic electrolytes. Okay, so based on the stability, we have to choose the electrode material. That is the first step, first strategy. Then second strategy, the replacement of organic carbonate electrolyte into solid polymer electrolyte or gel or hybrid polymer electrolytes. Then these are two options will be there for improving the safety and cyclability. Understood? So we know the safety issues arises due to the organic electrolyte and lithium dendrite growth will be there. Understood? So the two issues, these two issues only leads the safety problems. Understood? So the two, how to overcome these two issues. So one is the electrode combination. Then second one is the replacement of the existing organic liquid electrolyte. That means the replacement of organic liquid electrolyte with more potential stability polymer electrolyte. That is with the high thermal chemical stability and high ionic conductivity polymer electrolyte systems. Okay. So polymer electrolyte systems I am telling you. Polymer electrolytes. So here we know that polymer electrolyte was chosen as an alternative to liquid electrolytes as well as. What is the advantage of polymer electrolyte? So no leakage, high thermal stability, high chemical stability, and flexible geometry. We improve safety. But drawbacks is here low ionic conductivity, especially at room temperature. Okay, compared to the liquid electrolyte. So we know that liquid is having high ionic conductivity, but leakage will be there. The leakage will be there, and corrosions will be there. Electrolyte lithium dendrite formation will be there. Electrolyte decomposition will be there. Then stability of the electrolyte. That is potential window of the electrolyte. That's many drawbacks are there. So in order to avoid that, the researchers have been focusing to develop the polymer electrolyte. So even though polymer electrolytes are having drawback, that is a low ionic conductivity, especially at room temperature. Understood? So this is the standard separator available in the market. Monolayer and triple layer will be there. What is the separator? That is a good chemical and mechanical. These are the properties of the separator. Good chemical and mechanical stability, low thermal stability. Okay. So how to improve the ionic conductivity? So my focus is to increase the ionic conductivity without sacrificing the ionic conductivity. I want to increase the chemical stability. I want to increase the mechanical strength. I want to increase the thermal stability. Understood? So these are all the most important parameters during the operation of the lithium battery. Understood? So not only the conductivity, so along with the high ionic conductivity, we have to focus on the thermal stability, chemical stability, electrochemical stability, and flexible geometry. Understood? Suppose if it is not flexible geometry, internal resistance will be there. That means that electrolyte interface effect will be there. So there interface effect will be there. Understood? Even though electrolyte is having high conductivity with the high thermal stability mechanism also, but interface effect will be there. Finally, we won't get any cyclic. That means you won't get any output. Okay, so based on that, to focus, in order to improve the ionic conductivity, I have developed the nano composite polymer electrolyte fibrous membrane. So this is the most important, the fibrous membrane. Fibrous membrane, that is web-like structure. Understood? So in order to avoid that, so in my PhD, I have developed the nano composite polymer electrolyte fibrous membrane. Okay, so I would like to share my some research. What is the result? Some results actually I would like to share with you guys. So that related to the development of nano composite polymer fibrous membrane. See here, this is a flow chart for the preparation of nano composite polymer electrolyte fibrous membrane. Understood? So already I told you. So this is the separator. The separators look like the fiber one. That is a web-like structure. Okay, that is a web-like structure mat will be there. This is the separator. Then I thought, so why not we have to develop the electrolyte like this? That means a dual. So the electrolyte, the membrane will act as electrolyte as well as the separator. So dual nature. Understood? But here, separator, the commercial separator, we can't use as an electrolyte. What is the reason? That is a low thermal stability, low porosity, and poor wettability. Whatever electrolyte we are using in the battery, so that won't absorb by the separator. That is a poor wettability. That is a drawback in the separator. So how to improve that? So I have to develop the fibrous membrane. Okay, that is a nano composite fibrous membrane by electrospinning. Various synthesis techniques have been using. Okay, so various synthesis processes have been using to develop the electrolyte membrane, but so the electrospinning is an effective technique to develop the fibrous membrane. So this is the most important thing. That is a novel technique. That is a spinning, electrospinning technique. Now actually, recently, people have been using this technique to develop the fibrous membrane for a different application. Okay, not only for energy conversion and storage devices, for different, even medical applications also we are using the technique. Even for making the cloth, also the electrospinning technique we are using. So this is the effective and now it is a novel technique. So by using this technique, I have developed the nano composite polymer fibrous membrane. Here, polymer blend electrolyte fibrous membrane I have written here. So what is a polymer blend? That is a mixing of two polymers. That is called as a polymer blend. Okay, but here in the flow chart we can see. So PVDF is one polymer and Pmma. That is, I am mixing two different polymers with a different composite, with a different ratio. That is a 90% of PVDF and 10% of Pmma. That is optimized one. Already a pilot study I did many times. So based on that pilot study, I have optimized this one. 90% PVDF co-HFP and 10% Pmma. So this is a polymer blend electrolyte fibrous membrane. What is the filler? Magnesium membrane. This is also novel one. That is a magnesium membrane, zinc element. No one uses. So during my PhD, I'm the first person to use this filler. Understood? Even I have published this paper in ACS also. Okay. So using this filler, I have developed the nano composite fibrous membrane. So these are all the electrospinning parameters. Okay, this is the instrument we are having in our lab, and this is the schematic diagram of the electrospinning process. This is the spinner. Here cylinder will be there. Here spinner will be there. And we have to apply the voltage due to the potential difference. Here, from the Taylor cone, that thin fibers is coming and depositing on the collector. Understood? So this the flow rate by a syringe pump, flow rate controlled by the syringe pump. So these are all the electrospinning parameters have been used to develop the fibrous membrane. So this is the developed membrane. Okay. So over the collector, we made the electrospun membrane. So it is look like paper, tissue paper. It is look like tissue paper, but the tissue paper is interconnected fibers. Okay, like look like what is it? Spider net. Understood? So I will show the same images how it's look like. Okay, then the developed membrane soaked in the 1 molarity of lithium LiPF6 ECDC. Okay, to develop the composite polymer blend fibrous separated from electrolyte membrane. See here. So how the pictures are showing here. So all the images. So all these images actually HRCM images of the developed fibrous membrane. So all the images shown. What is it? There's an interconnected web-like structure. Okay, with ultra fine fibers. So even each fiber in the nanometer range. Understood? So even by interconnecting the each fibers, that is interlaying of each fibers method, what is that? Generate the porous structure between the two layers. That is the two fibers. Here more porous also will be there, and more what is the electrolyte absorption as well as retention capability also will be there. Understood. So this is the HRSM of the developed membrane. Here A to indicate the pure, and B1 is the polymer blend. That is a PVDF, 90% PVDF and 10% PMA. And this is a filler, various amount of filler disposed polymer membrane. That is, what is that? 2%, 4 weight percentage, and 6 weight percentage, 8 weight percentage. So different weight percentage of fillers I have disposed in the electrolyte solution, disposed in the polymer solution, and I made the nano composite fibrous membrane to increase the thermal stability as well as the mechanical strength as well as the electrolyte uptake. Understood? So here, so on the next pictures also, that is a polymer blend fibrous membrane with another filter, that is zinc aluminate. Understood? So here, so okay, after prepare the electrospun fibrous membrane, this is the morphological structure. So after prepare the fibrous membrane, see here. So each fiber indicates the nanometer. Here, the complete scale is 10 micron. So here, of each one is 1 micron meter. See here, just let us consider one fiber. Just keep it here, 1 micron meter. So around I think less than 100 nanometer only will be there each fiber. Okay. Suppose if you are increasing the diameter, if you increase the average diameter of the fiber, what will happen? That porous will be lower, and if porous will be lower means what will happen? The lower quantity, that is a lower amount of liquid electrolyte only can able to absorb. So that is also a problem. So we want a sufficient quantity of electrolyte for moving the ions, and to generate the for that actually we have to generate the more porous. Okay, not only the porous, we have to increase as well as the thermal as well as the mechanical strength. Okay, that's why we are adding the fillers in the polymer solutions. Understood? Okay, after prepared membrane, this is the prepared membrane, cut into the circular disc based on our requirement. Okay, then the cutted circular disc, that is the cutted membrane, as prepared membrane. The cutted as prepared fibrous membrane, we have to soak in the electrolyte solution and wait for some the equal interval of time, and the excess amount of electrolytes just we put the excess amount of liquid electrolyte by tissue paper. Then we have to prepare the electrolyte solution. This is the as prepared membrane, and this is the polymer nanocomposite polymer blend electrolyte with the electrolyte. See here, what is the difference here? This one is a pure white, and after soaking the electrolyte, see it is looking like transparent. What will happen? See, in this already electrolyte is there. So due to the porous structure, the membrane can be able to absorb the sufficient quantity of electrolyte. Understood? So this is the thickness measurement gauge. With the help of this instrument, we can measure the thickness. That is 82 micrometer. The thickness of the membrane. See here how thin. So if you make the thin membrane, so better compatibility between the electrodes and electrolyte. Understood? Then okay, after making the electrolyte solution, then first we have to prepare the electrospun membrane, then soak in the electrolyte, then we have to develop the polymer blend electrolyte fibrous membrane. After making that, we have to do the fabrication. So fabrication of CR200.6. Okay, so this is the picture of the fabrication. So step by step I showed you. So this is the active material preparation. That is slurry. So the slurry, the active material slurry, we have to put over the aluminum foil by using the doctor blade, then drying and cut into circular based on our requirement. Then we have to fabricate like this inside the glow box. There is a positive electrode. What is the positive electrode? Lithium metal. Now this is a positive electrode, active material coated positive electrode, and a negative electrode is the lithium, and the electrolyte is a nano composite polymer and polymer. This electrolyte acts as a separator also. So only 3 components. With the help of 3 components, we are fabricating the CR2032 concept. Okay, this is the glow box. Actually, I have fabricated the battery inside the glow box in our lab only. So we are having this facility to fabricate the battery. Okay, so after fabricated the battery, first we have to check the open circuit voltage of the battery, OCV. Okay, so with the help of multimeter, I measured the open circuit voltage of the fabricated battery. So point cell battery, for checking purpose, Swajlag also we made. So just we are checking the output of the battery after fabrication. So what is that? 2.68 volt. This is the discharging state. Okay, if I am making the charging, so it will come around 4.2 volt, 4 volt. Understood? So this one after fabricating as prepared, as fabricated back. So we are checking the OC. There is a 2.75. Now the fabrication is complete. Okay, the fabrication also got success because actually we are getting the OC, open circuit voltage. Understood? Now after fabricating the battery, first we should know the electrochemical performance. So okay, that is battery testing. So first we have prepared the membrane, then converted into the electrolyte, then fabrication. Okay, after fabrication, first we have to test the battery. How to do the test? Okay, so what is the instrument we are going to use to test the battery? So battery cycle tester. That is a battery testing. So we are using the bit probe. So this instrument is available in our lab. So for testing the fabricated battery, bit probe. So this is an excellent instrument to find out the capacity. That is to find out the cycle life. That is cyclability. So how many cycles the battery can withstand. Okay, so this is a battery. So this is the schematic diagram of battery testing. Anode, cathode, and electrolyte will be there, and load, current, and voltage. Okay, so we have to apply the current, charging and discharging, and we have to check the voltage also. This is the schematic diagram of the battery testing and the C rate. So before going to the testing, first we should know the parameters, C rate. So even actually, see, and the commercially available battery also, over the battery, the specification has been written. So what is the specification? That is C rate, this voltage, current rate. That is what is the current ampere. So 1000 ampere or 1 ampere or 2 ampere. So all the specification has to be written over the battery. Okay. So how to find out the specifications? So after fabrication, before going to test, first we have to set the parameters. Okay, then one by one parameters we have to apply while testing. Then we have to come to the conclusion. So this battery is withstand up to the particular C rate, and this battery delivers this much current. This is the voltage. Understood? So these are all the important parameters will be there. So first we should know the parameter C rate. What is the C rate? C rate is nothing but the current rate, the rate at which the battery is charging or discharging relative to its capacity. So after fabricating the battery, we have to test it by applying the external current. So that is the current rate. We have to apply some minimum current for charging and discharging. That is a 0.1 C rate, 1 C rate, 2 C rate, 5 C rate. Understood? That is that number indicates the fast rate. Okay. If you are applying low current, it will take more time to charging and discharging. If you apply high current, the time consumption is very less for charging and discharging. Okay, suppose if you are not giving the sufficient time for charging and discharging, the cells also won't. What is the cycle that the process, the reduction and oxidation process also won't complete. So we have to give the sufficient time for completing the reaction, and we have to find out by applying the different C rate. Okay, that is 1 C rate, discharging or charging 1 hour, 2 C rate, half an hour. That is fast one. 5 C rate, 12 minutes. That is 0.1 C rate, 10 hours. Here, these are different, 10 times lower. The 1 C rate and 0.1, 10 times lower. Understood? The 2 C rate means just higher. Okay, so how fast we are charging and discharging, we are applying the current. And what are the terminologies associated with use of the charging and discharging? That is state of charge, depth of discharge, and cycle number. What is the state of charge? That is a maximum charge. So one battery, how to charge it? So what is the maximum voltage how to charge? Up to the maximum they have to charge. Okay, that is the state of charge. That is a percentage of maximum capacity that is remaining unused one. So depth of discharge. What is the end of the cell voltage? Cycle number. How many cycles the fabricated battery can withstand? Okay, even 1000 times I can charging and discharge. So 2000 times I can charging and discharge. So that numbers we have to identify from this testing performance. Understood? So this is the behavior, that is a performance. The charge discharge curves actually look like this, voltage and time. Okay, that is this one is a discharging and this is the charging curve. This is a charging and this is a polarization curve. The polarization is a ohmic. The resistance loss will be there, activation loss will be there. Understood? The effect of C rate and discharge. That is a, suppose I fabricated one battery. That battery I have charged and discharged with a different C rate. So capacity and voltage. Different C rate. How the capacity is varying. See here. That is a C by 2, C, 2C and 5C. That is C by 10 means 0.1 C rate. That is one C requirement, that is charging and discharging within 1 hour. Suppose C by 10 means charging and discharging within 10 hours. So I am giving the sufficient time for charging and discharging. See here, C by 10 at lower at a higher time, lower current. So the maximum capacity is delivered. Okay. So based on this, so what I have fabricated the battery, that fabrication also I did the electrochemical performance. See here. Here ohmic resistance is very low. What I fabricated the battery because of the thin electrolyte membrane. So that compatibility is better. So suppose thick layer I made it. So that is the interface effectivity, that the interface effect gives the ohmic resistance. See here. So from this we can come to the conclusion also the ohmic resistance also very less. See here capacity also is higher. And also same battery I have fabricated with the commercial cell guard. See here, the compared to the commercial cell guard, what I have developed the nano composite polymer given shown higher capacity. Okay, given high capacity. So 0 weight percentage and 5 weight percent. That is without filler and with filler. 5 weight percent magnesium aluminate and 5 weight zinc aluminate given a higher current capacity. That is cell guard is 149. Even 30 cycles I did. So even after 30 cycles also the capacity retention will be there. Okay, then similarly the cycle performance of the nano composite, cycle performance, so after 30 cycles. Okay, so this paper also have published in the INX Polymer Journal, and the ACS also have published. Okay, Journal of Physical Chemistry B in 2015 I have published. Okay, similarly electrochemical personal polymer blend electrolyte. So already I told you that is a single polymer, that is mixing of two polymers. So I investigated the electrolyte, I have investigated the conductivity, then the thermal stability, chemical stability, electrochemical stability, and fabrication and electrochemical performance. So complete studies I did for the development of nano composite polymer 5+ membrane. Okay, now I am coming to the emerging battery technology. Okay, the emerging battery technology. So this is the most important thing. Okay, so I told you the available rechargeable batteries in the market. So among available rechargeable batteries, lithium batteries having high energy density, even small size and lightweight compared to the batteries. And I highlighted the issues and how to overcome the issues. Okay, then by developing the polymer like membrane, then I have developed the polymer fibrous membrane, and I have shown some of the highlighted results also. Then electrochemical performance also I showed you. Then how we have to do the performance, everything we see. Okay. Then emerging battery. What is the difference? Emerging battery is compared to lithium battery. Lithium battery. Okay. So there now the emerging battery technology is very different compared to the lithium batteries. Okay. Here metal air batteries will be there. Here air is the fuel. Understood? Suppose here the normal atmosphere air we are using as a fuel for redox reaction. So that is the attractive thing. That is the unique thing in the emerging battery technology. Okay, so we don't want to develop the cathode material for increasing the capacity. Clear? So even though the cell voltage is lower than the lithium battery, but here the theoretical energy density is more. That is more than 10 times higher than the lithium battery. Understood? The cell voltage is lower than the lithium battery, but capacity, there is energy density is 10 times higher. Understood? See here. This picture here, theoretical and practical energy density will be there compared to the other rechargeable batteries. The zinc metal layer batteries, that is zinc or lithium, the lithium-air batteries. This metal, so the metal is varying. Zinc we can use it, lithium we can use it, aluminum we can use it, magnesium we can use it. So different type of metal we can use it. But here anode we have to change it. Then cathode, that is air. The air is here fuel. Clear? So this is the attractive thing in the emerging battery technology. But even though, so this is not commercialized, this is not yet come to the, this is not yet commercialized for practical applications. Understood? Because many issues are there in this metal air battery. Many issues. So even, so if you are focusing on anode, so there also issues there. Electrolyte issues are there, cathode issues are there. But the energy density is equal to the gasoline. So that is the attractive thing. So because of the energy densities, the worldwide researchers have been focusing to develop this battery, metal air battery, that became the commercialized for electric vehicle application. That is the most important thing. So we know that. So shortage of fossil fuels. So we are looking for the alternative source. So now everyone having interest to purchase the electric vehicle application. For electric application, what we are going to use? The battery. Okay. So for next generation electric vehicles, metal layer batteries becoming a commercialized. So therefore, the researchers have been focusing to develop the novel materials for metal layer batteries. Okay, not only the anode, electrolyte, cathode. In cathode, many issues are there. So in coming slides, I will tell you what are the issues existing in the metal layer batteries. So, so what I have focused here. So even electrolyte also have developed some membrane. Electrolyte have developed even bifunctional electron catalyst. There is air cathode electrode will be there. I will tell you in the coming slides. So there is an attractive thing. So now researchers, actually very limited researchers have been focusing to develop this material. Okay, so even I think upcoming researchers may concentrate this field also. Okay, so here it can be used as the best power source for acceleration electric vehicle application. Classification: primary and secondary metal layer batteries. Again, so how the lithium batteries or the batteries can be classified? Primary battery and secondary battery. Similarly, the metal layer batteries also can be classified into two primary and secondary batteries. Okay, so that is a primary batteries we cannot use it, and secondary batteries we can use by repeatedly. Even secondary batteries can be classified into two. Okay, that is mechanically rechargeable and electrically rechargeable. So that is an attractive thing in the metal layer batteries. Okay, even the secondary batteries can be classified into two. That is mechanically rechargeable and electrically rechargeable. So what is meant by mechanical rechargeable? Okay, this is, so we know that. So battery having the components anode, cathode, electrolyte separately will be there. Understood? Here anode is the lithium. For example, lithium metal batteries, anode is the lithium. Zinc air battery means anode is the zinc. Clear? So air is the same. Even lithium-air or zinc air or aluminum-air or magnesium air, whatever thing is there, that is air cathode is the same and anode is the changing. So based on that anode, we are telling lithium-air, zinc air, aluminum-air, iron-air. So different air metal air batteries will be there. Understood? So how the secondary batteries can be classified? Mechanically rechargeable and electrically rechargeable. So mechanically rechargeable is nothing but we have to manually we are replacing the anode as well as the electrolyte. So that is a mechanical rechargeable. Understood? Suppose we are having one container. So in the container, that is anode, electrolyte, cathode, that is cathode, air cathode will be there. Not simply cathode, air cathode will be there. Because so air is the source here, air is the fuel. So air is coming through the cathode and reactions, redox reaction is happening inside the cell. Understood? So mechanical rechargeable is so air cathode as it is, we have to keep it in the container. Only we are manually replacing anode and electrolyte. Okay. Suppose after discharging, corrosions will be there. Then electrolyte discharge products will be there. That is electrolyte gets decomposed. So what will happen? Just I am recycling. That is I am reconstructing. That is I am replacing the anode and I am removing the electrolyte from the cell. And I am inserting the new anode and electrolyte. That is a mechanically rechargeable. Clear? So now electrically rechargeable. Second is electrically rechargeable. So electrically rechargeable, what is that? So whatever I fabricated the batteries, that is same. By applying the electric potential, by applying the source, external source, I am making charging and discharging. That is the electrically rechargeable. Clear? So anode, cathode, electrolyte acid is same. By applying the external source, I am making the redox reaction. That is a charging and discharging. That is electrically rechargeable. Okay. So what is the mechanism of rechargeable metal layer? So this charging and discharging will be there. I told you oxygen is the source. So metal and this is the air cathode. So the air cathode is nothing but the porous cathode will be there. In the porous cathode, bifunctional catalyst will be there and gas diffusion layer will be there and current collector will be there. 3 layers will be there. The 3 layers can be arranged in the sandwich type. That is a bifunctional catalyst, current collector and gas diffusion layer. 3 layers will be there. That is a big challenging to construct the air electrode. So that is a big challenging in the emerging battery technology. Air electrode configuration. So that is a separate topics will be there in metal layer batteries. Electrolyte, separate research will be there. Then anode, that is a modification of anode, different, separate. So even many issues are there. So we have to overcome all the issues for making the commercialization of the metal layer batteries for electric vehicle application. That is the main actual motto for our researchers. Okay, this is the mechanism. And how does lithium-air battery work? This is the lithium-air battery. So I told you, lithium-air battery means the anode. The anode is the lithium metal, and cathode is the air electrode. Then air electrode means nothing but the porous air electrode. That is, a porous carbon will be there, catalyst will be there, and the oxygen diffusion layer, gas diffusion layer, GDL layer will be there. So in between, electrolyte will be there and separate will be there. So this is the electrochemical reactions happening in the lithium-air battery. So similarly, zinc-air battery. So zinc metal, and in the zinc metal, see here, in zinc metal, aqueous electrolyte solution, and this is the non-aqueous. Because the lithium is highly reactive with aqueous. So we can't use the aqueous also. If we are using aqueous, here we have to make the protect layer over the lithium metal. Okay, so this is one non-aqueous, this is aqueous one, zinc metal. Because zinc we can use normal atmosphere also. So this one actually compared to lithium, more abundant and easily we can handle also. So that's why actually people have been focusing to develop the zinc metal air batteries for application for electric vehicle. Cost wise is low and handling also is very easy and more abundant. So that is a more attractive compared to the lithium. Okay, so nowadays the researcher has been focusing to develop the zinc metal air batteries. So here electrolyte, that is aqueous electrolyte, separator and catalyst will be there. So I told you this air electrode, catalyst will be there, and porous current collector will be there, and oxygen diffusion layer. Through the gas diffusion layer, oxygen is coming. The oxygen is normal gas. The normal atmosphere, oxygen is available in the normal atmosphere. The oxygen is coming. Okay, the oxygen is getting reduction. That is reduced. When the electrons is coming through the external circuit, the oxygen gets reduced. That is, the oxygen reduction reaction is happening. So here in the metal air battery, oxygen reduction reaction, oxygen evolution reaction. That is a redox reaction here. Reduction and oxidation reaction is here. But in lithium batteries, we call it as redox. But here, OR and O here. That is, oxygen is the source here. Oxidation reduction and oxidation evolution. Oxygen reduction is nothing but discharging. Oxygen evolution is nothing but charging. These two processes is happening. These two phenomena is occurring in the air electrode. Clear? So this is the anode and this is the cathode, and this is the working mechanism of the zinc battery. So similarly, hydrophilic carbon layer with electrode catalyst. Hydrophilics. What is it? Hydrophilic and hydrophobic. So coming slides, I will tell you the hydrophobic. What is it? Hydrophilic? We know that. Okay. So if water is absorbing, that is hydrophilic. If water is not absorbing, that is hydrophobic. Okay. So here, so we are using the normal atmosphere. The oxygen is taking from the normal. Here humidity will be there. So what will happen? So this humidity, that is water content, may enter through the porous structure and it spoil the electrolyte as well as the anode. So to avoid that humidity, we have to use the hydrophobic layer in the outer surface. So air electrode will be there, configuration will be there. Here this is the outer facing surface and this is the inner facing surface. This inner surface should be the hydrophilic and outer surface should be the hydrophobic. So why it is hydrophilic? Here electrolyte we are using. Electrolyte is nothing but aqueous electrolyte. So hydrophilic means automatically this layer, this electrocatalyst layer is more saturated with the electrolyte. So here aqueous electrolyte is saturated with the electrocatalyst. The electron transfer pathways is happening very fast. But here hydrophobic should be there to prevent the moisture. Okay, moisture absorption. So now I am coming to the lithium-air battery, that is architecture. So based on the electrolyte, the lithium-air battery can be classified into 4. That is aprotic, aqueous, solid state, and hybrid. Okay, so based on the electrolyte, I am telling you, the lithium-air battery can be classified into 4 based on the electrolyte. So what is that aprotic? Aprotic means organic electrolyte. Okay, that is organic liquid electrolyte. Lithium metal, porous air electrode, organic. That is coming under the aprotic. What is aqueous? Okay, so by replacing the aprotic, aqueous electrolyte we are using. So while we are using the aqueous, what will happen here? One protecting layer will be there over the lithium metal. Clear? So we know that lithium metal is highly reactive with the water content. That is moisture. Okay, suppose without protecting, if you are using the aqueous, what will happen? Explosion will happen. Understood? So here we have to protect the lithium metal. So here modification you have to do. You have to protect the lithium conducting membrane and the electrolyte will be there. Okay, this membrane should be there here hydrophilic. Okay, so the solid state electrolyte. Okay, but just so solid polymer, solid electrolyte or solid polymer electrolyte we are using for fabricating the lithium battery. That is solid state. Hybrid means both the solid as well as the electrolyte. That is organic solid electrolyte as well as the solid state polymer. Okay, so that is coming under the hybrid. Okay, so the working principle of zinc-air batteries. So discharging and charging, how during discharging anode, what is the reaction is happening? Cathode, what is actually reaction is happening? Overall reaction. So this is the zinc electrode and this is the air electrode. Here zinc ions will be there whenever the electrons is transferring to the external circuit. Here zinc ions is passing. Here zinc is coming. Zinc is coming here, and here hydroxide will be there, and KOH will be the electrolyte. What will happen? So zincate means zinc OH. Zinc OH. This is zincate ions. Zincate ions will be zinc OH. So this is a discharging product. Okay, discharging is happening. Then charging, what will happen? The zincate ions, just oxygen is releasing, the zinc is coming out, and water is releasing. So that is the charging process is happening. See here, zinc and 4OA, 2 electrons is releasing. That is anode is happening, and cathode 4H, the oxygen is going out, water is coming out, and 4 electrons going. Then again anode will come. Then the zinc will come. Okay, this is a discharging and charging process happening in the rechargeable zinc-air batteries. Okay, the parasitic reaction is zincate ions. So we have to concentrate to dissolve the zincate ions. Okay, issues and challenges. Already I told you many issues are existing in this Mclaren batteries. What is the poor ORR and OER reaction kinetics? Already I told you oxygen reduction reaction and oxygen evolution. This is discharging and this is the charging process. Okay, so these two processes are poor. Okay, electrolyte decomposition will be there. So during the discharging process, parasitic reactions will be there. The electrolyte decomposition possibility is the pore clogging. What is that pore clogging? The insoluble discharge products will be there. For example, zinc-air battery, zinc-air lithium-air battery, lithium peroxide will be there. So that the insoluble discharge products will go and block the porous structure. So if the porous structure is blocking, so there is no possibility to enter the oxygen from outside and gets reduced. Okay, so these are all the issues existing in the Mclaren batteries. And what are the challenges we have to do? That is a stable electrolyte we have to focus on. That is, the electrolyte should be stable. That means the electrolyte should be stable means the electrolyte should be more, oxygen ion diffusion will be there. That is a solubility. Oxygen ion solubility will be there, diffusion will be there. Okay, then porous cathode structure. So easily oxygen should come, should pass through the porous structure and reduced, and that reaction is happening fast. So the porous cathode structure we have to develop now. Highly active bifunctional catalyst. That is, oxygen gets reduced. So that is whatever the discharge product is producing. So we have to soluble the discharge products with the help of bifunctional catalyst. Then lithium anode protection. If you are using aqueous electrolyte, we have to do the lithium anode protection. So these are all the challenges existing in this Mclaren battery. So based on these challenges, I have developed some electrolyte membrane as well as the bifunctional catalyst. Okay, electrolyte challenges, carbonate-based electrolytes, are stable. So these are all the basic things, how to solve this. Ionic liquid, solid polymer electrolyte. So based on this challenge, I have developed the hydrophobic polymer electrolyte fiber. This is the first time. Okay, this is the first time I have prepared the hydrophobic polymer electrolyte fiber. How to develop the hydrophobic? Okay, so what is the precursor I have taken? So we know that PTFE. So I want to develop the polymer electrolyte fiber. So how to increase the hydrophobic? So we know that PTFE is a highly hydrophobic. Okay, so just I did the pilot study. I have disposed the various amount of PTFE in the polymer fibers. That is a PTFE, polytetrafluoroethylene. So PTFE is highly thermostability, highly mechanical strength, and highly hydrophobic. So PTFE is the thermopolymer. That is high strength thermopolymer. Understood? So that PTFE particles I have disposed in the PVDF solutions for making the hydrophobic membrane. So why I have to make the hydrophobic membrane? So I am using lithium metal as anode. So we know that. So whenever oxygen is coming from the atmosphere, the humidity can possible to enter through the pore structure. The humidity will affect the lithium metal. So lithium rendered growth will be there and corrosions will be there. So lithium is highly reactive with the moisture. So there explosive will happen. Okay. So in order to avoid that, hydrophobic electrolyte number I have. Okay, by electrospinning technique. So these are all the parameters I have used to develop the fibrous membrane. And this is the results actually what I developed the membrane. So structural studies I did and thermal stability DSC also I did to find out the thermal stability and conductivity also I have measured for the development membranes. So here the contact angle also I did, water contact angle. So I want to know the hydrophobic properties. So by using the water contact angle, I have checked the hydrophobic properties. See here, by changing the PTFE content, the hydrophobic also is changing. That is here. See here. So here, electrolyte uptake as well as the contact angle. Okay, by changing the PTFE content, electrolyte uptake, I am optimizing the electrolyte uptake as well as the contact angle. Electrochemical stability also, this paper also I published in the next paper. Then challenging, air electrode challenging. So we know that air electrode also great challenge will be there. Air electrodes is nothing but bifunctional catalyst, current collector, and gas diffusion layer. 3 layers will be. That is combination of 3 layers called as the air electrode. So air electrode configuration is a big challenge. So in that, I have focusing on the development of bifunctional electrode catalyst. So what is meant by bifunctional electrode catalyst? So what is the commercial catalyst we are using? So far, development of non-precious. Then generally precious metals and noble metal oxides have been using as electrode catalyst to facilitate the water and OER reaction. So it is having drawbacks, that is high cost due to the scarcity and poor stability. So the researchers have been focusing to develop the non-precious bifunctional electrode catalyst based on transition metal and metal price and cobalt-based metal oxides. So what is the drawback? Poor electrical conductivity and lower surface area. How to improve the electrical conductivity? So I want to modify the bifunctional electrode catalyst. Okay, to improve the electrical conductivity. What are the modifications I have to do? That is different structured metal oxides I have to prepare with the conductive graphene or nanotubes. So the first the modification. Second modification, I can develop the coercion structure. So third modification, I can develop the metal organics. These are all the modifications. Even many types of many techniques have been available to modify the bifunctional electrode catalyst for enhancing the electrical conductivity and the active sites also. Okay, that is surface area to increase the surface area also. So even based on the review of literature, even have chosen have developed some novel materials through the through combustion as well as one part hydrothermal process also I did, even electrolytes. So here, okay, we don't have time also, but first I am going to cover. Okay, so this is the synthesis process I have developed the bifunctional electrode catalyst. This is one part synthesis of hydrothermal process. Okay, this is a graphene oxide. The graphene oxide prepared by Humboldt method and disposed into water, and precursors have taken disposed in water. Then both just ultrasonication I did. That is a sonication probe, and that what is a transferred in the Teflon sealed. That is autoclave. Then heated up to 180 degrees for 12 hours. So I have developed the microstructs. That is a flower-shaped microstructs. So that is the beautiful. This is a novelty of this work. So see this picture. So I will show that this is the schematic diagram. So this is the schematic diagram of synthesis process. This is urea assisted one part synthesis I did. So urea is the reducing agent here, and this is the what is that? The filler also I did. What is that? Precursors. For example, nickel cobalt oxide, copper cobalt, the transition metal oxide. This is nothing but transition metal oxides. Okay, that is a hybrid. That is a transition metal oxides with a graphene. And this is the graphene sheets will be there. So this is a schematic diagram. See here, this is a graphene sheet. It's an ultra fine thin graphene sheet. See here. See ultra fine thin. This is a 500 nanometer. See here. So this thickness of the nanosheet is around 1 nanometer, 2 nanometer. That is a thin nanosheet. That is a look like transparent and wrinkled sheets will be there. So that is the novelty of the graphene nanosheets here. So we know that graphene is highly electrical conductivity. So over the graphene sheets, I am decorating the transition metal oxides for enhancing the electrical conductivity, for enhancing the surface area and the reactions, reactive active sites also. Okay, see here, this is the pure metal oxide. See how the microshrubs I have developed. See here. So the microshrubs is nothing but the microshrubs which is what is that, interconnected with the one-dimensional nanorods. See here, the TEM image I will show you. The TEM image I will show you. So here, this is the TEM image of the microshrubs. The microshrubs which is interconnected with the one-dimensional nanorod. The interconnected pores between the two spherical particles will be there. See here, in the nanorod, spherical particles will be there. That porous structure also will be there. That is a porous structures between the two spherical particles. Okay, these porous structures can enhance the oxygen. That is what is the electron transfer pathways. Electron transfers actually increase electron transfers and reactive active sites also will increase. Okay, so this one here, this is a different concentration of a transition metal oxide decorated in the graphene sheets. That is a different concentration. CCO 50 R2O will be there. Okay, that is a 50 R2O means that is a 50 milligram of R2O, 100 milligram of R2O, 200 milligram of R2O, and 500 milligram of R2O. The metal precursor is the same. So by changing the concentration, by changing the amount of graphene content, so how the synergistic effect. So actually my aim to investigate to analyze the synergistic effect between the transition metal oxides and the graphene sheets. So because of this synergistic effect, how the electron conductivity is increasing, how the surface area is increasing, how the electron pathways is increasing. There is an electron transfer pathway, how they increasing. So my aim to analyze this effect. Okay, for that purpose only, I have where is the different content of R2O, the different content of R2O decorated metal particles. This is the TEM image of the pure transition metal oxides, and this is the graphene sheets decorated metal particles, and this is the SAD pattern. Okay, so after reporting this bifunctional catalyst, so I want to check the electrocatalytic performance. Okay, so electrocatalytic performance, bifunctional activity, bifunctional catalyst. Bifunctional means that is OR and OER process should be there. So whether it is a OR and OER process is happening or not, I want to check it. So I want to analyze the catalytic performance. That is oxygen reduction and oxygen evolution reactions. So here this picture, this figure shows the oxygen reduction reaction polarization curves. Okay, so different the overall polarization curves carried out and the 0.1 molar of KOH electrolyte solution. There is oxygen saturated electrolyte solution at a different rotation speed. Okay, so here the platinum is a counter electrode and the silver is a reference electrode and modified what is a classic carbon. That is modified classic carbon means that is what is activated. So okay, I'm going to cover. So here at 1600 RPM, I actually have to analyze the catalytic performance, and by knowing the OER and what is that? This is a Tafel slope. From the Tafel slope, we can kinetic current also we can calculate it. Okay, so here see here, there's a ring current and discurrent will be there. So I want to find out the number of electron transfer pathway and a percentage of hydrogen peroxide production. So this is the general formula to find out the number of electron transfers and a percentage of hydrogen peroxide productions. Okay. Now similarly for other compounds, spindle structured compound. So I have studied this. I have showed the structural properties and surface morphology. Then OR and OER also I did. The onset potential. So here, so we want to develop the lower onset potentials. So we have our aim to find out the bifunctional catalyst should be lower onset potential. So for that we have to do the modification. Okay, clear. So for the different modifications, so I want to achieve the lower onset potentials compared to bare one zinc copper oxide. That RGO decorated zinc copper oxide is a lower onset potential and high current density. Okay, see here. This is the OR and OER polarization will be there, and a lower onset potential OR and higher onset potential of OER. And this is also structural and HSMU, another bifunctional electrocatalyst, and electrocatalytic performance of the NCO I did, and I have studied the number of electron transfer and percentage of hydrogen peroxide production also. So I have published in the Composite Part B engineering so recently. So in this
Yes, sir.
Happy and challenges of it. Yes, sir.
No, sir. No, it was cut. That's why I just.
Then development of hydrophobic polymer electrolyte fibrous membrane for Mclaren batteries. Okay, so already I told you electrolyte is the major problem will be there in the battery Mclaren battery. So I want to develop the hydrophobic polymer electrolyte fibrous membrane to prevent the moisture content, especially for a lithium-Air batteries. So this one no need to worry about the zinc-air batteries. So if we are developing the lithium-air batteries, we have to focus on the electrolyte as well as the lithium metal protection to avoid the moisture. Okay, then development of non-precious spindle structure bifunctional catalyst to enhance the reaction kinetics, that is oxygen reduction and oxygen evolution reaction. These two reactions are the most important in the battery technology, that is emerging metal air battery technologies, especially because see, we are utilizing oxygen from the atmosphere. So without catalyst, the oxygen won't reduced. So we have to develop the effective bifunctional catalyst to reduce the oxygen at a lower onset potentials. Okay. Then OER also for charging purpose also oxygen evolution reaction also should happen. So we want to develop the bifunctional electrocatalyst for metal air batteries. Okay. Finally, I'm coming to the acknowledgement. So I thank to Dr. Puducherry Fellowship for Financial Growth through Major Research Project Grant. I thank to DSD sir for providing the financial support in the form of Major Research Project Grant. And I heartily thank to Dr. C. Venkateswaran, mentor, professor and head, Department of Nuclear Physics, University of Madras. And finally, I heartily thank to Professor S. Austin Sundaraj, mentor, Department of Energy, University of Madras, Community Campus. And I heartily thank to Professor M. Satyanarayana, my PhD supervisor, Department of Physics, Puducherry University. Finally, I thank to my collaborators for providing the research facilities. Thank you. Thank you for your attention.
Thank you, sir. There is one question: why Pmma is used?
Yes.
In
so
blend.
Yes. So even the PVDF coach of polymers are having higher crystallinity compared to the PMMA. Okay. So for increasing the conductivity, we want more amorphous structure. Okay. So instead of PMMA, I am using the PVDF coach of polymers. The crystallinity nature will be there. So because of the crystallinity, we cannot it cannot move the ions freely. So we want the amorphous structure. So by adding the PMMA, so we know that PMMA is a more amorphous nature and low thermal stability also. Okay, so by adding the small quantity of the PMMA, there is an optimization of crystallinity as well as the mechanical strength. Okay, so my aim to decrease the crystallinity. Okay, one is the higher crystallinity, another one is the lower crystallinity. If I am mixing this both the properties of the polymer, so I am optimizing the crystallinity. Okay, so if reducing the crystallinity, so I want to increase the conductivity. So that is my aim.
Yes. Sir, can you throw some light in using CNT based electrodes for lithium-ion batteries?
Carbon nanotube. Yes, even actually like graphene, even I have used graphene for the modification. So instead of graphene, carbon nanotubes also we can use a modification. Okay, so even compared to the graphene sheets, carbon nanotubes and one-dimensional structures. So their electron the diffusions will be faster. That is, a lithium-ion diffusion is more faster than the graphene sheets. So we can use the carbon nanotubes for anode, for cathode, or for cathode modification. Even actually nowadays, instead of lithium, so even SiO2, even metal oxide based CNT modification materials have been using as anode materials.
Thank you, sir. Thanks for your elaborate explanation about you have touched about all type of researches that you have done.
Thank you, sir. Thank you, sir. Thank you, sir.
It will be helpful for people who take up research in the field.
Yes.
Thank you.
So that's why actually I have given the basic concepts of the batteries. Even actually upcoming researchers are there, so they want to develop their skills and they want to choose the title. So in which area they want to focus it. So based on that, actually I have given the presentation.
Thank you, sir. Thank you a lot. Thanks.
Thank you, sir. Thank you.
Dear participants, we will start the next session by 11:45. We have a very short break. We will meet by 11:45. Sir, there is one more question. Padmaraj sir, one more person is asking,
tell me,
trifluoroethyl methyl accelerate in place of Pmma.
Trifluoro, sir. Yes. Actually, first we have to find out the properties of the particular polymers. Even so, suppose two polymers we are going to blend it. So in which basis first we have to blend it? So one is the higher crystallinity or higher thermostability or higher metal status. One should be the lower crystallinity, lower mechanical strength, and lower thermostability. So if you are mixing these two, what will happen automatically? Then optimizations will come. So the one is the top or the one is the lower. So if you are mixing both the polymers, so that property should come at the center. Okay. So before going to use this trifluoroethyl methyl acrylate, so first we have to find out the crystallinity properties, then mechanical and thermostatic. Then we can choose whether we can add in a small quantity or higher quantity with the PDS portion. So that is the best thing.
One more question was there. How can we fix process parameters in electrospinning?
Yes. Actually, this is what is the very interesting question, sir. This one. Even then electrospinning, actually, I mentioned that 6-7 parameters. Okay, the first parameters is the distance between the spinneret and collector. Okay, then second one is the flow rate. Okay, then third one is the applied voltage. Okay, then fourth one is the conductivity of the electrolyte solution. So these 4 or 5 parameters are depending to form the fine ultra thin fibrous membrane. Okay, so first what we have to do, first we have to fix the distance between the spinneret and collector. First you fix it. Okay, so before going to now actually we want to do the optimization. First you have to fix the one distance between the spinneret and collector. Okay, then flow rate also you fix it. Just you check the voltage, applied voltage. Okay, suppose the voltage also depends on the viscosity of your polymer solution, not electrolyte, polymer solution. So if it is more viscous, we have to apply the more voltage to overcome the viscous force. So we know that viscous force will be there, that is the Taylor force. So we have to apply the voltage to overcome the viscous force. Okay, so suppose we are applying the lower voltage. So the applied voltage is not enough to overcoming the viscous force. We can't get the fiber, that is, we can't get the jet from the Taylor force. So we have to apply the voltage with respect to the viscous. So if you are having the viscometer measurement, viscometer instrument, we have to find out the viscosity of the solution. So based on the viscosity, we have to optimize that the voltage. We have to optimize the applied voltage. So by trial and error only, we have to fix the parameters, especially for the electrospinning.
Thank you, sir.
Thank you, sir.
Thank you. And, thank you, Madam Bornali, Bora ma'am. The basic explanation of the batteries was wonderful. I think others have thanked also. What is the lifetime of battery?
Yes. Sir, no, actually, no, in this presentation also already I told you the battery testing performance. Actually, after fabrication only we have to test it the lifetime battery. So that the lifetime of the battery differs on the lithium ion. So I am talking about the lithium ion battery. So the lithium ion diffusion and diffusion in and out. Okay. So during the design, suppose first cycle. So the lithium is passing from anode to cathode. That is the lithium diffusion during the charging. So whatever the lithium is deposited on the cathode, that the lithium is coming out from the cathode to the anode. Understood? So this number of lithium ion diffusion and out. So first cycle is 100 lithium ion is going to cathode and first charging. So out of 100, 95 or 90 will come out. Okay, in second charging, second discharging and second charging. So even out of 95, 90, 85, 90. So that the lithium ion diffusion and coming out there. So this is the parameters actually for fixing the lifetime of the battery. Suppose 1,000 cycles it is coming. So at the end of the 1,000 cycles, there is no lithium ion coming out from the cathode for the charger.
Thank you, sir.
Thank you, sir.
Many have thanked you. I should also thank the participants.
Thank you, sir. Thank you very much.
Thank you, sir.
Thank you.
For the next session.
Okay.
Yes, sir. Thank you, sir. So we will wait for another 5 more minutes to let the next speaker join.
Yes, sir.